In this video, we're going to talk about calorimetry, which describes the directionality and quantification of heat transfer. And as we all know, heat's always going to transfer from a warmer system to a cooler system until materials reach equilibrium. That's assuming that there's no other additional input of energy. Okay, so if we think of our hands as being the system, and we think of a bucket of ice water as being the surroundings. If you put your hand into ice water, you know that the temperature of your hand is going to drop. And that's because energy is transferring from your hands, the system, to the surroundings, the ice water. And that would be described as an exothermic process. So anytime the energy is leaving the system, it's considered exothermic. If you think of a situation where you then ran your hand under some warm water or put your hands in a warm water bath, you would end up having heat flow from the warm water to your hands, and therefore the system would be absorbing energy, and we would call that an endothermic process. So whenever heat is transferring into the system, we describe that as endothermic. Now, when we're talking about the amounts of energy being transferred, there's a couple ways to do it. In America, we usually use calories, and a calorie is defined as the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. But when you look at a nutrition label, you're not really seeing little c calories. You're seeing big C calories, food calories, which is really a kilocalorie. So that would be the amount of energy required to raise a kilogram of water 1 degree Celsius. So it's significantly different. But right now, you're in chemistry class, and we live under the laws of physics, so we're going to use the unit joule. And we know that 1 calorie is equal to 4.184 joules. Now, when we're talking about heating and cooling materials or transferring warm objects into cool objects or vice versa, we need to take into account the identity of the material. So each material requires a different amount of energy to change given mass of that material, its temperature. So water has a very high specific heat capacity, which is defined as the number of joules to raise 1 gram of water's or 1 gram of that material's temperature by 1 degree Celsius. You can see here water is 4.184 joules per gram degree Celsius. And if you think back to the definition of a calorie, that should make sense. However, most materials are significantly less. So you can see here that aluminum is less than 1. It's like 0.9 joules per gram degree Celsius. But if you look at the table to the right, you can see that most metals are even significantly lower. And the higher the molar mass of a metal, the lower the specific heat is for that metal. So the less energy it's going to take to change a gram of that material by 1 degree, its temperature by 1 degree Celsius. So I do just want to differentiate specific heat, which we don't usually say specific heat capacity. We usually just say specific heat to avoid confusion, with another term called heat capacity. Now, if you look at this example here, you can see that you have a cup of water and a bathtub of water. Right? They both would have the same specific heat because it takes the same amount of energy to change 1 gram a given material by 1 degree Celsius, but their total heat capacity is significantly different. A hot bathtub is going to be able to transfer a lot more energy to another object than a cup of water at that same temperature. So just to differentiate heat capacity and specific heat capacity, we use this example. Now, when we're solving problems talking about heat transfer, we're going to do an example right here. We're going to use the equation that the heat transferred Q is equal to mCdelta T. So M represents the mass of a given material, C is the specific heat, and delta T is the change in temperature, which can be defined as the final temperature minus the initial temperature. And so in this problem, what we're going to do is we're going to look at the amount of energy lost by a sample of aluminum. So you have 25 grams of it, and it cools from 310 degrees Celsius to 37 degrees Celsius. Now, I went and looked up the specific heat from a previous slide of aluminum to know that it was 0.897 joules per gram degree Celsius. But all you really need to do is plug in the values in this equation. So the heat transferred is going to be equal to the mass, which is 25 grams, times the specific heat, which is 0.897 joules per gram degree Celsius. And you multiply that by the change in temperature. Notice that the change in temperature is negative because it's decreasing, right? And that's also going to imply a loss in energy, right? So we're going to have a calculated value for heat transferred of negative 6,120 joules. Notice that the grams cancel out and the degrees Celsius cancel out as well. So this is how you can approach simple calorimetry problems. And in the next video, we're going to look at heat transfer between two systems. We're going to quantify the amount of energy gained by one and lost by another.